Hello, today's topic is geometric progressions. So the next topic we're going to look at are geometric progressions. These are slightly different to arithmetic progressions. I'm going to write down a few and you see if you can tell me what the pattern is. So one geometric progression I might write is 1, 3, 9, 27, 81. Another geometric progression I might write is 8, 16, 32, 64, 128. Another geometric progression that I might write is 10, 5, 2.5, 1.25, 5/8. Can you tell me what the next term in each of these progressions is? What do all these progressions have in common? They are geometric. How does that compare to arithmetic? You've probably worked it out, but rather than having a common difference between each one, here the difference is 2, and then the difference is 6, and then the difference is 18. So the difference changes every single time. It can't be the difference, but rather what we've got here is what we call a common ratio. Here I am multiplying by 3, multiplying by 3, multiplying by 3. And so the ratio from one term to the next is common. We don't have a common difference, common ratio. Here our ratio is times 2, etc. Now here we could think of our ratio as dividing by 2, but we like to always think of these as a multiplication. So rather than thinking of that one as a division by 2, let's think of it as a times a half. So each time we are halving, we are timesing by a half to get to the next one. All right, I'm going to rewrite out that first one so that we can look at it in a bit more detail. 1, 3, 9, 27, 81. We've got the same notation for geometric progressions as arithmetic progressions. So I can call this one T1, and this one T2, and this one T3, and this one T4, and this one T5. Can we come up with a rule for Tn? Let's think about it. But before we go any further, we're going to need to work on some notation. In our arithmetic progressions, we had T for referring to the term, and we had D for our difference. In this case, we're going to be talking about T1 as our first term, and we're going to be talking about R, lowercase r, is our common ratio. So can we work out a rule using T1 and R? Well, T2 is obviously going to be T1 times R. And T3 is going to be T1 times R, and T4 is going to be T1 times R times R times R. And what you'll notice is that all of these are T1 times some amount of R's. How many R's are there? There is one less than the term number. So in this case, term 4 has 3 R's. Generalizing this, we can say that the nth term, Tn, is going to be our first term, T1, times that many R's. How can we write out that we're multiplying that many R's? Well, we should know that to the power of is repeated multiplication. So this is R to the power of, and how many are we going to have? We're going to have n minus 1. So that's our formula for a geometric progression. The nth term is equal to the first term multiplied by the common ratio to the power of n minus 1. So in this particular progression, 1, 3, 9, 27, 18, can we work out what the 10th term is? Well, the 10th term is equal to the first term, 1, multiplied by the common ratio, 3, to the power of 9. So I can get out my calculator and I can say, what is 3 to the power of 9? And 3 to the power of 9 is 19,683. You can see that these progressions get bigger much faster than arithmetic progressions. Let's have a look at this one here. Can we work out what the 10th term of this one is going to be? Well, we know that our 10th term is equal to our first term, 10, times our common ratio, which is a half, raised to the power of n minus 1. So that's to the power of 9. So I can type that into my calculator. 10 times a half to the power of 9, and I get 0.0195. A lot of the same skills that we did with arithmetic progressions we can do with geometric progressions, and they should be fairly similar aside from the formula that we're using being slightly different. To give you an example of that, let's have a look at this question. If the third term in a sequence is 2 and the sixth term is 128, what is the eighth term? So let's write down what we know. Before we go any further, we'll write down this formula again. So just down here where I can see it nice and handy, Tn, the nth term, is equal to our first term multiplied by r to the power of n minus 1. What have we got in this particular case? Well, we know that our third term, so that's t3, is equal to 2, and that's equal to t1 multiplied by the common ratio, which we don't know, to the power of n minus 1, and n is 3, so this is r squared. So 2 is equal to r squared, and we also know that our sixth term, t6, is equal to 128, which is equal to term 1 times the ratio to the power of n minus 1. N is 6, this is our sixth term, so that's to the power of 5. Where do we go from here? Well, with arithmetic progressions, we solved them with simultaneous equations. Here, the simultaneous equations are a little bit trickier, but to work out what r is, I can do a division. Let's have a look at what the sixth term divided by the third term is. We get 128 over 2 is equal to t1 times r to the 5 divided by our first term times r squared. Let's have a look at what happens here. Term 1 cancels out with term 1. If you know anything about your index laws, you'll know that r squared cancels out with r to the 5 and leaves us with r to the 3 on top. And 128 divided by 2 leaves us with 64 is equal to r cubed. Now I'm going to need to do a cube root on my calculator, and I get r is equal to 4. So I've worked out what the ratio is. To work out what the eighth term, which was the original question, let's also work out, we can plug our r value in there, but let's work out what our first term is that we can plug in there. And to work out our first term, we know that t3 is equal to 2, which is equal to t1 times r squared. So that tells me that 2 is equal to t1 times 4 squared, which is 2 is equal to t1 times 16, dividing both sides by 16 gives me 1/8 is equal to term 1. So my geometric progression can be defined as the nth term is equal to 1 over 8 times 4 to the power of n minus 1. Now to work out our eighth term, we simply just plug n equals 8 in there, and we get 1 over 8 times 4 to the power of 7, which I can type into my calculator, and I get an answer of 2048. And I've finished. Now's a great place to stop and have a go at the next set of exercises. Welcome back. The next thing that we're going to look at is the sum of terms in a GP. Now I'm going to spend the next couple of minutes showing where the formula comes from. In this course, you don't really need to know that. You don't have to follow along with what I'm going to do. So if you're feeling lost at any stage, don't worry with this stuff. The algebra is getting a little bit complex. The most important thing is the final product. Just like in an arithmetic progression, it's useful to be able to add up all the terms. And so we're going to learn a formula for that. Let's think about what it might be. Well, our sum to n terms of a geometric progression is going to be our first term, which is t1, plus our second term, which is t1 times r, plus our third term, which is t1 times r squared, plus our fourth term, etc., 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 all the way up to t1 times r to the power of n minus 1. Now, I'm going to multiply all those by r and get another equation that is also true, t1r plus t1r squared plus t1r cubed all the way up to t1 to the power t1 times r to the power of n. Now both of these equations are correct, and so if I do a subtraction of one from the other, let's call this one equation 1 and this one equation 2, and if I do equation 1 subtract equation 2, you'll notice that in equation 1 we've got this thing, This one subtract this one will cancel out. This one subtract this one will cancel out. This one subtract this one will cancel out. Everything, that one subtract that one is going to cancel out. Everything is going to cancel out apart from the t1 that we've got at the beginning minus t1 times the r to the power of n that we've got at the end. Thus, the sum to n terms minus r times the sum to n terms is equal to the first term minus the first term times r to the power of n. If I divide, let's take out the sum of n terms as a common factor, and I get 1 minus r is equal to t, and let's take out t1 as a common factor, and I get 1 minus r to the n, and let's divide both. Remember, I'm trying to isolate the sum to n terms, and so let's divide both sides by the 1 minus r, and I get the sum to n terms is equal to t1 lots of 1 minus r to the n all over 1 minus r. Now, that's a formula that works. We could have here, instead of doing equation 1 minus equation 2, I could have done equation 2 minus equation 1, and that gives us, the process still works and gives us a bunch of different things, and we end up with a slightly different formula, which is the sum to n terms is equal to the first term times r to the n minus 1 all over r minus 1. Either of these two equations work. It doesn't matter which one you use. It's usually the case that we use this one for when r is less than 1, and we use this one for when r is greater than 1, but it doesn't really matter. You only have to use one of them. They both work perfectly well all the time. It's just a case of typing things into your calculator appropriately. Let's have a look at the geometric progression 3, 1, 1/3, 1/9, and let's work out what the sum of the first 8 terms are. We could work out what each of them are individually. We could continue going with the sequence and then use our calculator to add each one of them up. But I'm going to use the algebraic way. So let's go with the sum to 8 terms is equal to, I'm going to use this formula here. And so that tells me that it's term 1, which is 3, multiplied by 1 minus the common ratio, which is 1/3, raised to the power of n. In this case, we're going to 8 terms, all divided by 1 minus, what's the common ratio? It's 1/3. This, doing some basic calculations, gives me 3 lots of 1 minus 1 over 3 to the power of 8, all divided by 2/3, which is 9 over 2 lots of 1 minus 1 over, let's quickly type into our calculator, what is 3 to the power of 8? And we get 6,561. So typing all that into my calculator, 9 divided by 2, lots of 1 minus 1 divided by 6,561 gives me an answer of 4.499. We could work that out as a fraction if we wanted to, but doing so is beyond the scope of this course. You'll be able to use your calculator to work out these ones. So that's a good place to stop the video and have a go at some of the exercises asking you to find the sum of some GPs.